Okay, now, rapid sand filters. So here's a cross section of a rapid sand filter showing how we can have sand that is being held up by gravel. This is kind of the older design where sand is held up by gravel. And the way you get sand held up by gravel is you put small gravel on top of bigger gravel, on top of bigger gravel, on top of bigger gravel, with the idea that each change in size, the pores of the next layer down are small enough so that the smaller stuff that's on top can't go down through the pores. And so you can end up having sand supported by gravel by doing that transition in size. And so that the sand and gravel can all make sense, perhaps. This is showing the filter in filtration mode where the influent water is going in, it's going up on top of the filter, it's going down through the anthracite, down through the sand, down through the gravel, out through this under drain system, and out to the effluent and to the clear well or to the distribution tank, and they're going to add chlorine and it goes on to the community. And there's also anthracite on top. This is very, very common, and often there's a lot of anthracite and a little bit of sand. It depends on the design. Here I show actually less anthracite than sand. And the anthracite has a larger diameter, right? It's 0.7 millimeters rather than the 0.5 millimeters for the sand. And it's also less dense. And that ends up being critical because what's happening when you backwash the filter, the water's going to go up through this filter so fast that it's going to fluidize it. It's the sand is going to be moving around, supported by the water pressure that's pushing it up, and all the sand and anthracite could potentially mix. But the sand terminal velocity is actually greater than the anthracite terminal velocity, and so the anthracite ends up on top. Okay, so that's how dual media filtration works. You get the larger grain sizes to end up on top, even though they were larger, but it's because they're less dense, so they settle slower. If you just had a sand bed and no anthracite, and you didn't sieve the sand to have it all be a similar size, so you had sand that was ranging from 0.2 millimeters up to 1 millimeter in diameter. And now you fluidize that sand bed, and then you let it all settle back down again. Which sand grains most likely end up on the bottom? The ones that were settling faster, right? So the 1 millimeter ones end up on the bottom, and the 0.2 millimeter ones end up on top. So you end up with this non-uniform stratification with the smaller ones on top. And our growing understanding of filtration is that the larger the pore size, the less the head loss is per amount of solids that you remove. So if you put fine sand on the top, the filter will develop head loss very, very quickly. And so it will have short filter runs. So what you would like is large sand on the top. And that's why anthracite is placed on top. Filtration velocities ranging from 0.7 to 2.8 millimeters per second. So that means that these filters are similar in size to an agua clara clarifier. Of course, one is in that range, right? And the backwash velocity is going to be a whole lot higher, roughly 6 times higher. And the backwash velocity is set to fluidize the sand bed. I want to just talk about backwash yet, just very briefly. So here's the same cross-section of the filter, and this time I've changed the valves, and there's wash water, which is clean filtered water, that's coming in from the other side of the filter. And now there's this trough that you probably saw before and you wondered what it was. So there's this black trough that's at the top of the filter, and that is exiting, and it's actually dumping the backwash water out onto your desktop, right? It's coming right out of the screen at you. And so water is going up through the gravel, sand, and anthracite, and the gravel has a high enough terminal velocity that it's not being fluidized, it's not suspended, but the sand and the anthracite are up there moving around. And apparently there's a link there to fluidized beds. You can, there's at least now a few videos on YouTube about fluidized beds or fluidized sand. There's even, I forget which YouTuber has a video of sand being fluidized using air. And it's worth looking at that just to see like what happens when you fluidize a bed. What's cool is when a bed is fluidized, if you put something on the top of that bed that's more dense than the bed, it will just sink right down through the bed. Matter of fact, that's how we tell if a sand filter in an agua clara plant is fluidized. We take a PVC pipe that is really, really long, and we drop it down onto the sand bed. And if it's fluidized, that PVC pipe will just nicely drop right into the sand bed. And if it's not fluidized, you can't push it in even if you try. Okay, so you can easily tell that way if the bed is fluidized. The question here is, why are we using wash water? Why are we using clean water, treated water, to backwash a filter? Why is this the conventional design, and why is it like so important? So look where the water's coming in at the bottom of the filter. We're putting clean water in at the bottom of the filter and running it up through the filter and out the top. When we quit backwashing, what water is on the bottom of the filter? The water that we just used for washing it. And so if we were to use raw water, for example, dirty water from our mountain stream to backwash the filter, then when we quit backwashing, there'd be dirty water coming at the very bottom of the filter, and that would be the first thing that would go towards our clear well to our customers. So that's why wash water has to be treated water. Only clean water should ever be on the effluent side of the filter. And agua clara with our STARS filter actually violates this. We don't use filtered water. We use clarified water, which is not quite as good. It's still pretty good. But that's one place where we kind of fudged the rules a little bit to be able to get a design that didn't require pumps in order to backwash.